Hello, my name is Vishwajit Shrikant Bhosle and I'm presenting the topic routing algorithms for 2D and 3D NOC architectures. So the motivation behind development of NOC is that due to technology scaling, more and more elements are included on a single chip. Therefore, complexity of system on chip architectures is increasing. In addition to that, heterogeneous cores are used more and more commonly. So these core, one of the core will have more processing power, the other will have less processing power. So their bandwidth requirements vary. So traditional bus architectures are no longer able to support these requirements. So the limitations of them are they have RC delay, they suffer from crosstalk, they are not scalable, and their bandwidth is limited. So network on chip, or NOCs as they are called, transfer data in form of packets. They follow a layered protocol stack similar to wide area networks. They contain processing elements, network interfaces, and routers. Processing elements basically perform manipulation on data. Network interfaces connect processing elements to routers, and routers route the data packet over the network. But they are different than wide area networks in that they have stringent area and power requirements. Topologies define how nodes are arranged and connected to each other in a network. There are three types of topologies: direct, indirect, and regular. Of all the topologies, mesh topology is the most popular because of its easy implementation. There are two types of switching: circuit switching and packet switching. In circuit switching, a dedicated physical path from source to destination is reserved for a data transfer. In packet switching, each packet can take different path from source to destination. Of all the packet switching strategies, wormhole switching is commonly used. Routing determines how packet will be delivered from source to destination. Which path will it follow? Routing can be differentiated as static or adaptive. In static routing, every packet from source A to destination B will follow the same path. In adaptive routing, the path is selected based on current status of network. In minimal routing, packets follow the shortest path from source to destination. In non-minimal routing, that's not the case. It is important to select the right routing strategy for the architecture to obtain optimum performance. Challenges in NOC routing are faults in the network, which are becoming more and more common with technology scaling, congestion due to uneven traffic distribution, deadlocks due to dependencies in resources, and live logs in which packets can't get to their destination. Some common strategies which are used to tackle these challenges are: for fault tolerance, fault awareness is used, in which neighboring nodes are made aware of an fault which has occurred. In deadlock, turn models are used where certain turns are prohibited to prevent cyclic dependencies. For congestion, awareness of congestion is used, and for live log, minimal path routing is used. Some basic NOC routing algorithms are XY routing, which is static, odd even, which is dynamic, and DYAD, which fluctuates between static and dynamic routing. In XY routing, a packet is forwarded in X direction until the column of destination node arrives. Then it is forwarded in Y direction. This algorithm is simple to implement. All packets from a source to destination follow the same path. Due to this, issue of congestion arises. This algorithm also has no measure to prevent deadlocks. These are some of the emerging algorithms which are presented in the paper. We will see them in following slides. First is global congestion aware routing algorithm. This algorithm has global congestion awareness as opposed to local awareness. in which only few neighboring routers are aware of their neighbor's congestion. It is used for 3D network-on-chip architectures. It works as follows. When a packet originates from a source, it contains congestion information of the source. As it travels, this information is supplied to other routers, and their congestion information is embedded in the header of the packet. It first routes the packet in XY direction and then in the vertical direction. It uses 2 bits per router to store the congestion information. As seen from its working, it can be seen that it has limitations on scalability because header of a packet can only store limited amount of information, and the amount of information stored increases with increase in size of the network. Therefore, a method to represent congestion with less data overhead can increase its scalability. This algorithm is for partially connected 3D NOC architectures. Its main objective is fault tolerance in vertical links. It uses a novel method of advertising for fault tolerance in vertical links. It uses elevator indexing system for advertising vertical links. Nodes with operating vertical links are assigned highest index number. These nodes transmit these indexes to neighboring nodes. The neighboring nodes then store these indexes values and further transmit these index values to their neighboring nodes after reducing the value by a certain amount which is predefined. If a node does not transmit index for a predefined time, then that vertical link is considered faulty. A router sends its packets in the direction with highest index value. Therefore, optimum routing is achieved. This algorithm turns every router into a context-aware agent, which is aware of its neighbor's congestion and operation status. It uses 2 bits to communicate information about congestion based on buffer utilization threshold. If the threshold is crossed, then neighbors are informed about it and they now need to find a new path for their packets. The immediate neighbors of the malfunction node are called expert agents, which communicate to other nodes about congestion or malfunction and also act as a guide to form new optimum path to the destination. The new path is formed by selecting the path with least load value obtained by nodes on the path. This algorithm decreases the number of healthy nodes sacrificed to avoid deadlock when fault occurs in a node. Information about faulty blocks is communicated to neighboring nodes and they form what are called defense zones, and packets are routed around the faulty blocks with the help of these defense zones. These defense zones are smaller in size compared to conventional faulty blocks, therefore it saves healthy nodes. It uses ceiling and floor registers in routers to store information which is required for formation of these defense zones. The following observations are made from algorithms presented in the paper. The algorithms presented are either mono or multi-objective. Deadlock freedom is present in most of the algorithm, although it is not the primary objective. They use similar set of strategies to solve the problems with some variations. For example, for fault tolerance, rerouting is widely used. For deadlock avoidance or freedom, turn restrictions and virtual channels are used. For congestion, adaptive routing and routing tables are used, which make use of congestion awareness. For live lock, minimal paths are used. It is also observed that the papers present results only on the objectives that they studied. Their implications on other metrics of the network are not presented. For example, an algorithm for fault tolerance might use rerouting for fault tolerance, and it might improve the fault tolerance of network, but its implication on congestion in the network is not given. It is also difficult to make comparison between the algorithms because they use custom simulators for the experiments. Most of the algorithms do their comparison with the XY routing algorithm.